Welcome to lecture 4.7 over the inverse trigonometric functions. We're going to start this lecture by reviewing just a tad bit, not really intense reviewing, but just me reminding you of some properties of inverse functions in general that you picked up from college algebra. Then we'll look specifically at the inverse functions of sine, cosine, and tangent. And if you have your calculator handy, you can look at the sine, cosine, and tangent buttons, and you may notice that as a second function to those keys, it looks like sine raised to the negative first power, cosine and tangent raised to the negative first power. Those are the inverse functions. And then we'll, do some calculation with it with our calculator, and then we will look at finding values for composite functions. Okay, so this first slide here is that memory jogger that I was telling you about, having to do with inverse functions in general. So you should remember the horizontal line test, and the horizontal line test tells us that if a horizontal line intersects the graph of a function no more than once, then that function is 1-to-1, and it has an inverse function. And of course, if a function fails the horizontal line test, that means it does not have an inverse function. If you have point AB that lives on function F, then the point, you flip-flop your X and Y values there, and that particular point that's flip-flopped lives on the inverse function. And we denote the inverse function as f to the negative first power. Now, this is not f raised to an exponent of -1. Which would make it like 1/f. That is not what we're looking at here. This is simply notation saying we're talking about the inverse function here. So I definitely wanted to point that out to you because that notation can be confusing to look at. So also, another characteristic that we have is that the graph of the inverse function is reflected across the identity line, which is the line y equals x. So I'll just draw you a quick picture of what that's talking about up in the purple space at the top. So if I have a graph here, I'll just use one of the common functions and its inverse that we encounter in college algebra. We oftentimes look at the function x cubed, which comes through and s's across the x-axis at the origin. And in our studies in 1111 or college algebra, we find that the inverse function is the cube root of x, which comes in like this and s's across and then goes off there. So this last statement that says the graph of f inverse is reflected over the identity line. The identity line y equals x is this line coming through here where the slope is 1. So you can see how that acts as a reflective mirror for a function and its inverse function. So is that all this business here clear, Mark? Jog your memory a little bit? Great. Okay, so we'll take our first case here of the inverse sine function. Now, hopefully you recognize that what is graphed here in front of you is just the sine function, and you can see it's labeled here, y equals the sine of x. And if I use the horizontal line test, which this dotted line running through is indicating, then if I don't put boundaries on my domain, you can see that the sine function fails the horizontal line test miserably. However, if I bind my domain or restrict my domain between one period of negative pi over 2, actually, I guess it's not a full period, rather half a period, to pi over 2. So if I restrict my domain to here, or any of these pi periods that fall on the half pies like that, you can see that if I restrict myself, I now have a piece of a function that passes the horizontal line test. In other words, I'm not passing through more than one point on that piece of the graph with a horizontal line. Welcome, Roy. I'm glad to have you tonight. So when we restrict our domain to these increments of negative pi over 2 to pi over 2, and in any of those multiples, we can begin to talk about having an inverse sine function. Are y'all ready to move forward from here? Okay, great. Even Roy, great. He just popped in and he's already ready to move forward. Okay, so this is just a little bit of information from your book stating sort of what we've just already said. The inverse sine function is denoted by sine to the negative first power. This should be reminiscent of our work with logarithms from college algebra, where we had if y equal, b to the y equals x, if and only if y equals log base b of x. So this is going to look sort of like the same thing. And also from college algebra, we learned when we are finding inverse functions, we flip-flop or reverse the x and the y. So notice we're restricting ourselves to that negative pi over 2 to pi over 2 for our domain. The x there tells us we're talking about the domain. So if we have this function y equals the inverse sine of x, that is synonymous with saying that's the same exact thing as if I have the regular sign of the flip-flop of those coordinates, so sine of y equals x. So we can interchange these, which helps us with evaluating inverse functions. Okay, so we're going to take a look at our first case, and this is the only one that I have set up to actually hand graph. The rest of the lesson will either be using tables or we'll just look at a picture, but I did want to go through and hand graph one of these for you just to keep you fresh on your graphing of these trigonometric functions. So I want to graph just good old y equals sine of x first, and I'm going to restrict myself to that domain of negative pi over 2 to pi over 2. Okay, so I actually put one more blank in my chart than I needed. I'm going to do negative pi over 2 as my first x value, negative pi over 4, 0, pi over 4, and pi over 2. And let me just show you on the graph where negative pi over 4 and pi over 4 show up. Halfway between negative pi over 2 and 0, that's negative pi over 4. And then halfway between 0 and pi over 2 is positive pi over 4. All right, so back from our unit circle and all the work we've done previously with all of this, you find that the sine of negative pi over 2 is negative 1. The sine of negative pi over 4 is negative square root 2 over 2. I went ahead and put that in my calculator. That's a wavy equal sign to say that's approximately negative 0.71, just to be able to put it on the graph. The sine of 0 is 0, and the sine of pi over 4 is positive square root 2 over 2, which is approximately, sorry, that looks terrible in that box there, approximately 0.71, and the sine of pi over 2 is positive 1. So I'm going to put this sine function on the graph with this restricted domain in orange. So I have negative pi over 2, negative 1, about right there. Negative pi over 4, negative 0.71, so just a little less than actually being down at that 1 mark. 0, 0, pi over 4, 0.71, and then pi over 2, 1. And we know that this has sort of a hump shape to it, so it sort of comes through like this, and then it's getting ready to top the hill there and go back down. Now, the wonderful thing about the inverse sine function is that we really don't need to do much work at all to figure out what our coordinates are. All I have to do, based on my definition of inverse function and how it acts, is flip-flop my x and y values. I forgot to label this. This is x and this is y, so this will also be x and y there. So I'm not even going to think about this. All I'm going to do is come in and flip-flop those coordinates. So negative 1, negative pi over 2, negative square root 2 over 2, and negative pi over 4, 0, 0, pi over 2, and pi over 4, I'm sorry, square root 2 over 2 and pi over 4, and 1 pi over 2. Well, we know that 1 on our x-axis, because we need to have a 1 and a negative 1 in there somewhere, 1 on our x-axis lives about right here. It's not quite pi over 2. Remember, pi is estimated at 3.14. So pi over 2 is going to be about 1.5 something, and then, we want 1, so we want a little ways, negative 1, so we want a little ways away from that negative pi over 2 towards the origin. Same thing on the opposite side. So this is 1, and this is negative 1 in here. And I thought I used a different graph. I'm sorry. I thought I had a graph that was more centered around the origin when I was creating this. I have a better looking graph on your note sheet, so hopefully you're able to graph this a little better than I can get to show up on the screen here. All right, so we have negative 1 pi, negative pi over 2. And once again, negative pi over 2 is about at, you know, roughly negative 1.5. So negative 1, negative pi over 2 would probably live about right here. Let me get my pink. About right here, very roughly speaking. And then negative square root 2 over 2 is equivalent to negative 0.7. I'm just going to put into my calculator real quick, pi divided by 4. Pi divided by 4 is 0.79 approximately, so it's going to live right towards the origin, right to the inside of pi over 4. So if I graph negative 2.2, I'm so sorry, negative square root of 2 over 2 and negative pi over 4, my negative square root 2 over 2 is 0.71, and so that's going to live about right there on the x-axis. And then I'm going to drop down pi over 4, which is 0.78 or 0.79, so about right here. Not quite negative 1. And then I also have 0, 0. And now I have square root 2 over 2, which is that 0.71 roughly, and 0.78, so about right here. Let's see. And then pi over 4, 1. So this comes through like that. And that's a really, really awful picture, but we've got a better one on the next slide. So hopefully it'll be clear as mud after we look at that other slide. But I did want to go through the graphing of it. And since we're restricting the domain to that negative pi over 2 to pi over 2, our range for our sine function, of course, is restricted to negative 1 over 1, which is true for any sine function, no matter what the domain is. It's unless you've translated it and moved it in the plane, you're always going to have that range of negative 1 to 1. And then we have just the opposite for the domain and the range of the inverse sine, or sine inverse function. So this domain, we went from negative 1 to 1, and the range was from negative pi over 2 to pi over 2. All right, Roy, you ready to move forward? Okay. All right, so here is a much prettier picture of the sine of x, which is in red there, and the sine inverse function, which is in blue. So I just included this so that you could have a nice view of what it looks like. But I really do think it was a good thing to remind ourselves about graphing those things by hand. Okay, at this point, I would like to bring up that sine inverse function is not the same thing as 1 over the sine of x. Just like that -1 floating up in the air is not raising to an exponent of -1, this is how you denote the inverse function. So what we get is that when y equals the sine inverse function of x, this is a symbol for if and only if it's the biconditional. So saying this is only true, and it's always true, when x equals the sine of y. So that's juxtaposed with y equals the sine of x raised to the -1st power. Just to refresh you on your exponent rules, a to the -nth power is the same thing as 1 over a to the positive nth power, as long as a is not equal to 0. So when we have y equals the sine function to the -1st power, that is indicative of 1 over the sine of x, which we found out a couple sections ago is the same exact thing as the cosecant of x. So hopefully that was helpful to kind of straighten everything out in your mind with all this notation here. Okay, so now we're going to talk about finding exact values for this, this inverse function or sine inverse of x. So we have steps that we can follow, which is nice, because it would be a lot of nasty calculation if we didn't have these nice tables, and the textbook company was not, or the publisher or author was not kind enough to give us nice neat values to work with here. So we're going to let theta equal sine inverse of x. We're going to, that's your first step. Your second step is to rewrite theta equals sine inverse of x as, we're going to flip-flop it and turn it to, oops, I did not mean to draw straight through that. We're going to flip-flop those coordinates and write it as the sine of theta equals x. And we've got to keep our restrictions here. So this is a table just showing the values taken from the unit circle here. And the third thing that you do is you find what value of theta, which is your x value in that case, what value of theta gives you the sine of x there. I'm sorry, the sine of theta. So I think this will be more clear when we actually look at an example. Okay. So we are given the task of finding sine inverse of square root of 3 over 2. Our first step is to simply rewrite. So we want to have theta equal to sine inverse, and we're trying to find the inverse of square root 3 over 2, or the inverse sine of square root 3 over 2. And now we're ready to flip-flop and say, okay, well, if this is true, then the square root of 3 over 2 has to equal the sine of theta. So just to remind you, we had square root 3 over 2 equaling sine of theta. And so how we go about this is we want to find out when the sine of theta is equal to square root 3 over 2. So I look down in the row that's labeled sine of theta, and I find that the angle in the domain of negative pi over 2 to pi over 2, whose sine is square root 3 over 2, is pi over 3. So that's stating it in words, or I could have said theta in this case is pi over 3. When I take the sine of theta, I get square root 3 over 2. Y'all good? Great. Honey, my microphone's picking that up. Okay, so just another example here. We are asked to find sine inverse of negative square root 2 over 2. So the first thing we're going to do is write our problem. Theta equals sine inverse. And for our x value, we're going to plug in negative square root 2 over 2. And now we're going to flip-flop our x and our theta. And that says negative square root 2 over 2 equals the sine of theta. Honey, can you please turn that down a little bit? Okay, so just as a reminder, we had negative square root 2 over 2 equals the sine of theta. So what we're looking for is the angle theta, that when we take the sine of it, it gives us negative square root 2 over 2. So if we look right here, the sine of theta is negative square root 2 over 2 when theta is equal to negative pi over 4. So written in words, the angle in our domain here, negative pi over 2 to pi over 2, whose sine is negative square root 2 over 2, is negative pi over 4, or theta is equal to negative pi over 4. Okay, so now we're going to take a look at the cosine function. And if we thought about the horizontal line test here with the cosine function, you may notice that if we restrict our domain from 0 to pi, that we will have an inverse function there. So our new restricted domain for the cosine function is going to be 0 to pi. Okay, So once again, just notation here. If we have that y equals the cosine inverse of x, that means that the cosine of y is equal to x. So it's that same flip-flop when you move between the cosine and the cosine inverse functions here. And notice here's our restriction on our domain, which is 0 to pi. And then we have restrictions, well, I say on the domain, actually this is range if we're talking about y's, but since we're talking about the flip-flop of it, hopefully that makes sense. And then in the opposite direction, once again, we're never going to go above or below -1 or 1. Okay, so I am going to grab a different color besides that blinding green there. All right, so here's a picture of the cosine function. We're familiar with that. Hopefully we're familiar with that by now. And we have the cosine inverse function here. So notice our domains and our ranges are exactly flip-flopped from each other there. And if we superimposed these graphs on top of each other, so if I sketched the cosine inverse function through here, and this is going to be a terrible sketch of this. Let's see, and then it goes to 1, to something like that. You would see, if these were actually not hand-drawn, that that thing reflects across the line y equals x. That is a characteristic of a function and its inverse no matter what functions you're dealing with. Okay, so this should look really familiar to you. It's the same exact process as working with the sine function. So I'm not going to beat a dead horse here and repeat everything I said for sine because it's the same. The only difference is you have a different restriction. And that's about, and of course, now we're looking at a table for cosine. So you want to let theta equal the cosine inverse of x, rewrite as cosine of theta is x, and then use your chart or your table to find the appropriate value. Okay, so we have, we're asked to find the inverse cosine function for -1/2. So the first thing we're going to do is rewrite our problem here. We're going to say, okay, theta is equal to, oops, started writing secant. Goodness, it has been a long day. Cosine inverse of -1/2. And now we're ready to flip-flop. This says -1/2 is equal to the cosine of theta. And now we're going to check our table to figure out, well, what value of the angle theta is -1/2? Okay, so I'm just grabbing a blue pen here. So once again, we're looking to figure out what value of the cosine of theta is equal to -1/2. And I see right here that when the cosine of theta is equal to -1/2, that theta is 2 pi over 3. So in words, the angle in my domain here, my restriction, 0 to pi, whose cosine is -1/2, is 2 pi over 3, or we could just say that theta is equal to 2 pi over 3. Mark and Roy, are y'all still good to go on all this? Yeah, this should probably feel like kindergarten after the past few sections we've been through, just being able to use a chart like this to figure out our answers. Okay, we've already made it to the tangent function. And if you're looking at your calculator, you should be getting excited because this is the last one that we have to go through before we do a couple of practice problems and then we're done. All right. Oh, I see the thumbs up, Roy. I hear you on that. All right, so tangent. Once again, horizontal line test. As long as we are restricting ourselves to one period, we pass the horizontal line test, meaning we do have an inverse function as long as our domain is restricted. And you can see that domain restriction here is from negative, and I'm using parentheses, not brackets here, because at those actual values of -pi/2 and pi/2, those are asymptotes, remember? So I have to use parentheses with this particular domain. But we can see that we are restricted to those intervals of -pi/2 to pi/2. Okay, so once again, our statement regarding the inverse, or the function of tangent inverse here, we have y equals the inverse function of tangent if and only if the tangent of y equals x. We have our restrictions here. And then that is going to not bind us in our range. Remember, that thing kind of looks like this all the way. So we're going from -infinity to +infinity in our vertical direction. And just to reiterate about the visual aspects of these inverse functions, if I superimpose the inverse tangent function over the tangent function, I'm going to get that S coming through something like this, which once again is awful because I'm hand drawing this, and it's going to reflect across that line y equals x. And that just is a flip-flopping of the coordinates that makes that happen. We are boogieing. Although we have 6 slides left to go, we are on the last page of our note sheet, which is awesome. This is probably the quickest lecture I've ever been through with y'all. All right, so same old here. I believe this is a blank maybe on your note sheet. Let me look. Yes. So you can fill that in. If we have theta equals tangent inverse of x, then tangent theta equals x. We have our restricted domain here. We're going to use the table that was gleaned from the unit circle. Okay, so before we actually, no, never mind, I'm going to hold off. I was going to say before we work this problem, I was going to write something up here for you. There's a slide that I should have included, and I should have included a piece of it on your note sheets, but I'll tell you what that is here in just a moment. Let's go ahead and work through this problem here. So we start out just simply writing our problem. We have theta equaling tangent inverse of -1 in this case. And if this is true, then this must also be true. -1 equals the tangent of theta. So once again, we had -1 equals the tangent of theta. So we're trying to figure out what value of the angle theta yields -1. And if we look here in our chart, the tangent of theta is equal to -1 when theta is -pi/4. So let's get in words, the angle in, notice we have parentheses here, -pi/2 to pi/2, because if we use brackets, that's saying include these values, and we know at those values there are asymptotes whose tangent is -1 is -pi/4. In other words, theta is equal to -pi/4. And I believe I have a typo on your notes. Your notes said to find tangent inverse of 1, so that would just be pi/4. The PowerPoint asked us to find -1. Sorry about that typo there. Y'all good to move forward? Excellent. Great. Okay, so these are the 3 inverse trig functions that we've discussed today. I really don't have much more to say about these except that I included them on your notes mainly as reference point for you. You have your domains and your ranges listed, the shapes of each of these things. This is probably one of those pages that you'll want accessible when you take your test over this information. Okay, so these next 2 problems here have you using your calculator. So there's really not much for me to show you. So to access any of these inverse functions, you have to hit the second key first. It's a blue key, and then hit either sine, cosine, or tangent. So you'll notice on your calculator you have your sine function there, and right above it written in light blue is sine, that's terrible, you can't see, is sine inverse. So I just used the calculator to figure these. Cosine inverse of 1/3, and it's going to open a set of parentheses, so just be careful and make sure you close your parentheses. It's not going to matter with these two problems, but when you start adding things on or dividing or whatever, you want to make sure you close those parentheses. And when I put this one into my calculator, I get that the inverse cosine of 1/3 is approximately, and it asks us to round to 4 decimal places, 1.2310. I do have to put the 0 on the end there because I did round to the 4th decimal place, and even though that doesn't change the value of it, that tells the reader that I have rounded to the 4th decimal place there. And then the tangent inverse of negative 35.8, the only thing I'll point out here is that you've got to use the negative sign, not the subtraction sign on your calculator. The negative sign is located at the bottom right-hand corner of your calculator. The minus sign or the subtraction sign is listed up the right-hand side with the other basic operations: addition, subtraction, multiplication, and division. So make sure you're using the negative sign there. And when you put that into your calculator, you get that that is approximately negative 1.5429. Do either of y'all have any questions about using your calculator to find these inverse functions or the values of the inverse functions? Okay, I'm not getting a response, so I'm assuming no questions on that. We'll go ahead and move forward with this last concept. Oh, I did include the slide. Yay, I just didn't include it on your notes. This comes directly from your book. It may be worth your while to write these inverse properties down on your notes. I actually printed out my own set of notes and I wrote it on there so that I could have it to work with composite inverse functions. So basically this first one says when I'm taking the sine of the sine inverse of x, that just leaves me with x. And notice you have to state that it's in that restricted interval. So I'm not going to go through and read all these to you because they always come out to x. That is a property of inverses that we studied in college algebra, that when you compose a function with its inverse or compose an inverse function with its function, or its partner function, you're always going to come out with x because you've undone everything that was being done to the variable. Does that make sense? Okay, Roy says yes and Mark says yes. Excellent. Okay, so to figure this first one out, I'll just give you the information from the last page. We have that the cosine of cosine inverse of x equals x, and that is on the restricted domain of -1 to 1, and cosine inverse of cosine of x is equal to x on the restricted domain of 0 to pi. So if I have the cosine of -1, I just need to look here and I see that 0.7 lives inside that restriction there. So the cosine composed with the cosine inverse of 0.7 is simply 0.7. Moving along, I have the sine composed with the inverse sine of x. That also gives me x, and that is the restricted domain of -1 to 1. And then I have sine inverse composed with the sine of x is x on the restricted domain of -pi/2 to pi/2. So, if you look here, pi lives outside of -pi/2 to pi/2. So what I have to figure out is, can I take the sine of pi, and if I can, will my range from the sine of pi live in the domain of my inverse sine? So I have the sine inverse. Well, the sine of pi, if you go back to the unit circle, the sine of pi is just 0. Now I need to look, okay, well, am I legal with taking the inverse sine of 0? And you can see that the inverse sine of 0 lives actually in both of those domains there. You pass over the origin with both of those. So looking at our unit circle, we have that sine inverse of 0 is equal to 0. Well, actually not looking at the unit circle for that, we know that the sine, that gives us, the sine of pi lives at 0, 0. So if I take the sine, which is the y value, if I take the sine of pi, I get 0, but the flip-flop of that is also 0. So that's where that came from. Was that confusing, or was that okay for y'all, for B? Okay, Roy says it was okay, and Mark says it was okay. Good, I'm glad I didn't confuse y'all with that one. Okay, last but by far not least, and we can use this same information for the cosine here for this last one. I'm taking the composite of cosine function composed with cosine inverse of -1.2. Well, notice the cosine inverse lives outside, lives outside of my approved, if you will, or my restricted domain. So this particular composite is undefined, because I can't even take the inverse cosine of -1.2 to get anywhere. To be able to take the cosine of whatever output comes from the inverse cosine of -1.2. So this entire composite is undefined. Gentlemen, that's all I have for you today, and we kept it under an hour. I think I'm going to go buy a lottery ticket. If y'all don't have any questions, I'll just thank y'all for coming tonight and tell you to have a wonderful evening and a wonderful weekend unless I see you at tomorrow's lecture. Roy, before you go,